Hello everyone. In this video we are going to look at kinematics of we call car-like mobile robots, or the ones that have this Ackermann formula applied to them. So as you know, in your car, uh, here assuming that the driving wheels are the rear wheels and the steering is done by the front, right, as most of the cars are, then as you know, when you go around a circle, the steering angle of the two tires on the front, the inner wheel, the one that is closer to the center of the curvature, and the outer wheel, the steering angle for them, if you call them delta I and delta O, they are not equal. Okay, so we have to basically turn each one of them differently. Also, the angular velocity, or the RPM, of these back tires also should not be equal as well. Okay, so the outer one should spin faster as it goes in a bigger circle, around the bigger circle, compared to what? The inner one. Because here, if R is the radius of the curvature, where the center here is this point we call ICC, or instantaneous center of curvature. If R here is the radius of that, and then the width of the chassis here, we call it the track width, is shown with W. One of these, which is the outer one, goes around a distance of R plus W over 2. The other one here goes on a circle with radius of R minus W over 2. And since they have to do it in the same amount of time, or with the same angular velocity theta dot, right, and V equals R times omega, if theta dot is the same, then since the radii are different, that means the velocity of the centers of these tires should be different. This one should have what? Should have a bigger velocity for at its centroid compared to the inner one. And that means this guy has to what? This omega O has to be bigger than omega I. It has to spin faster, because this one is equal to omega I times radius of the tire, right? And here we show it with R sub t. And this guy is equal to omega O times RT, okay? So that means your omega O has to be bigger than omega I. And on the other hand, I'll show you that delta I, the steering for the inner tire, should be bigger than what? The steering for the outer tire. And again, the reason is this one has, the outer one has a bigger radius, so it has a smaller curvature. And to compensate for that, you have to steer less. So this one is done, the difference between this delta I and delta O is done by the steering mechanism. So your steering mechanism can make the two tires compensate, right? And one of them has a bigger angle than the other. The change in the RPM is done through what we have here in the back of the call, which you all know it, and it is called what? It is called the car differential. Okay, so it's the differential of the car which allows the two tires in the back axis to what? To rotate at different RPMs. So we want to look at this kinematics here, and we want to look at the changes of the x and y position. If we show the x and y position of this differential with just xc and yc in general, or x and y, and the angle of this chassis with angle theta, we're going to look at how these three parameters are changing what? Over time. Here we also have an inertial frame, xi and yi. These frames are fixed. So these inertial frames are fixed. This xc and yc are what? Attached to the car, okay? So this xc, yc is what? It's attached to the car. But the inertial one is fixed with respect to the ground. And the angle between them is theta, and we're going to look at the change in that theta as well as the change in x and y. So xc dot and yc dot. Now, we show the velocity of this point here, also the velocity of the car moving forward by v of g. So we call this center point here g. Another parameter we have involved in the car is the length of this chassis, which we call it basically the wheel base, L. So that is another parameter of the geometry of the car. And finally, we have this delta, and delta is the angle of the steering mechanism that you apply through the steering wheel. Okay, so when you turn the steering wheel and you command it so much of turn, that is this delta. So this delta is what you really need to have so that the center of these two inner and outer wheel passes through the circle with radius r. Okay, we call it the command delta. This is what you have to have in order to go through that circle. Okay, but again, you have what? You have delta I and delta O, where delta I is bigger than the inner one will turn more than what you pass through the steering wheel, and the right one is gonna go less than that. Okay, so there is this inequality between these angles, and we're going to look at formulas for calculating them, which we know them as what? As the Ackermann formula. So let's go ahead and dive into it. Okay, so I did a little bit cleaning here, and now it's time to what? It's time to derive the formulas. So if you look at the angle delta I, the inner wheel steering, if we want to calculate this delta I, that's the same as this angle, which is drawn between what? Drawn between this line, which is perpendicular to that direction of the tire, as well as what? This basically y-I axis, which is perpendicular to what? To this one here, to this xc and yc. Since these two are perpendicular to those two, therefore the angle between them is the same, so they are both delta I. Now, how can I calculate delta I? Well, here, for delta I, you look at, let me choose a different color here, maybe green. For delta I, you look at what? You look at this triangle here, this one. If you look at this green triangle, and look at the tangent of delta I, it's this side, which is L over this side. And what is this side? That is R minus what? Half of the W. Okay? So that is tangent of delta I. And for delta O, we have a very similar calculation, except the triangle is different. So for delta O, we use this triangle. Again, this side of it is L. This side here is now what? It is R plus W over 2. So L divided by this is tangent of delta O. Okay? And one thing we can do is we can take a reciprocal of both sides, so we get cotangent of delta O and cotangent of delta I. And if we subtract, the denominators are both L, so it's going to be R plus W over 2 minus R minus W over 2. The R's would cancel. You get W over what? L. So another way that you can get a formula out of these two is to say cotangent of delta O minus cotangent of delta I is W over L, which is basically like a spec ratio for your chassis, right? So that means the longer the car and the narrower the car. So if the car is very tall like that, that means these two will be very close to each other, okay? Because this ratio goes down, right? Assuming that you keep W fixed and increase L, the ratio goes down. That means these two angles would be closer. But on the other hand, if the car is kind of square shaped, more like this, now here, one of them has to what? Turn quite a bit more than the other one. So it's really depending on this W here and here on the L, right? So a wide car needs the big difference between the two angles. And if it's a narrow car and long, it can have a smaller difference between them. Okay, so this is the Ackermann formula, either these two or this subtracted version. You can call it Ackermann formula or Ackermann geometry. Okay, so this is the major one, but there are other formulas that we need to drive and we need to discuss about them. So what about the command? How much of steering do we need to have? Okay, for that, we look at this triangle here, this middle one, which is this one. And this time, the tangent of delta is simply L over R, because this distance is simply R. Okay, and so you get this formula here that from here, how much of command do you need? Delta is tangent inverse of what? Of L over R. So if I know the length of my car, the chassis, the wheelbase, and I know on what kind of radius I'm going to turn. So this radius is what? This is the radius of the turn, the traffic circle, whatever it is, okay? Radius of turn, okay? If I know this number and I know the length of my car, I can find out that how much of steering I need at the steering wheel, okay? Now, it might not necessarily be exactly to the amount of the steering wheel, because between the steering wheel and this delta, you will have a what? You will have some gear reduction, okay? And you will have a mechanism. But this delta command is clearly proportional to what? To what you command at the steering wheel, okay? So if it's not equal to it, then definitely proportional to it. And another technical term that just wanted to let you know, the ratio of delta I. Remember, delta I is bigger than what? Delta I is bigger than delta. Delta is bigger than delta O. Okay? The ratio of this delta I over delta, right? The steering of the inner wheel to the command, we call it gamma, or we call it the steering ratio. So just wanted you to know about that. Okay, another formula that I want to talk about are the similar versions of this formula, this Ackermann formula that we had, this one. But here, instead of subtracting cotangent of delta O minus delta I, we subtract the cotangent of what? Delta O minus delta, or delta I minus delta. Because remember, from here, what is cotangent of this angle if we write it? The cotangent of delta is R over L, right? So when I take reciprocal of that, also they all have denominator L, and if we subtract, then I get cotangent of delta O minus cotangent delta is W over 2L, and similarly cotangent of delta minus delta I is also W over 2L. And what's good about it? Well, from here, from this top one and the bottom one, I can find delta O and delta I as a function of delta. You see here? The delta shows itself in the formulas for delta O and delta I. And you might say, why would you do that? Don't we have these two formulas here on the top? From these two formulas, I can easily what? I can easily find my delta O and delta I. Yes, so why do we need these formulas 2 and 3? This is true if you exactly give it the steering angle that you should be giving it, right? So that is assuming that you exactly give it the steering delta required, so it goes through that radius R and with the wheelbase L. Do you always do that? The answer is no. You probably have seen a lot of times that you are going around the traffic circle and initially you don't steer enough, and you see that you are now going on a bigger circle and you're kind of moving toward the outer edges of the traffic circle, and sometimes you are steering too much and now you're getting closer to the center of the traffic circle. Then you try to adjust it, right? So not always the delta that you command to the steering wheel window, this delta is not always equal to what? It's not always equal to tangent inverse of what? L over R. If you do that, that is perfect. But you don't, because what? Because even if you know your L of the car, you don't have a measurement device ahead of time to measure the radius of the traffic circle. So you don't always exactly know how much of steering you should be giving to the car. Okay? So if you don't give it exactly that number, if you give it something other than that, what would be the value for delta I and delta O? Right? At that moment, how much is it? These two formulas will give you those. Right? And I'll show you in a demo right now in a minute. And I show you what happens when you steer more or less than what is required, which is this number. What's going to happen? Okay, I'm going to show you in a simulation. But just know that if you don't, these formulas 2 and 3 can be used. So these formulas 2 and 3 are always valid. Okay, so that was about the angles, the steering angles. What about the RPMs? Remember, we said that the RPMs of the outer and inner wheel are not equal, and the outer wheel, omega O, should be rotating faster than the inner wheel because it goes on a bigger circle at the same time. Is there any formula for that? Yes. So how? Well, here we use the simple formula that we learned in dynamics, and that is, if an object spins about a circle and the radius of that is r and the angular velocity is theta dot, velocity at any point is what? Equals r times omega, right? So that's what we know from dynamics. So we're going to use that right now. And we are going to what? We are going to look at the velocity of the center of the outer wheel and the velocity at the center of the inner wheel. Okay, these 2 points that I showed you earlier, this one and this one. They are both spinning about this ICC point, and the distance for them, remember, for one of them was r minus w over 2. For the other one was what? It was basically this distance here, which was r plus w over 2. So these radii times this theta dot should be the velocity of those two centers, and these are these formulas that you can see. On the other hand, if we assume there is no slipping, so here there is an assumption, and that is what? No slipping. If there is no slipping under these tires, then velocity of the center of the outer wheel equals to the RPM of the outer wheel times radius of the tire, and similarly for the inner wheel, it's equal to angular velocity of the inner wheel, omega I, times the radius of the tire. And here we assume the two tires are the same radii, RT and RT, or we can call them RT left and RT right, or outer and inner in general. So here, for simplicity, we assume they are the same. Now, if you look from here, I can what? I can go ahead and solve for these two unknowns, omega I and omega O. Now, what do I have here? One thing I have is R, W. Now, theta dot I don't have. Theta dot I don't have, but guess what? I can get it. Why? Because if you look at the center, the velocity at the center of the chassis at the back is Vg. So this Vg should be equal to the radius of it, which is r, times what? Times this theta dot. And this Vg is determined by how much you push on the accelerator, okay? And the condition of the road. So this Vg is one of the parameters under your what? Under your control. So here we have to add another formula, and that is what? Vg equals r times what? Theta dot. Okay? Now, let's go ahead and use this formula, see what we get. Well, first thing first, we subtract the two formulas. If we subtract the two formulas, what's going to happen? The r terms would cancel. You get a w times theta dot, and it's going to be rt times omega o minus omega I. So you get this top formula. On the other hand, the velocity of this center of this axis is equal to the average of this inner wheel velocity and what? The outer wheel velocity. So if you call this VI and you call this VO, this VG is what? The average of VI and VO. Let me do a little bit cleaning. So it is like this, okay? This is what? This is the average of VI and VO. Where did I get that? From simple rigid body kinematics, right? If you have a point between two other points in a rigid body, exactly the middle point of the two, the velocity of it is also the average of those two velocities. That's not really anything new. So if this guy is called VO and this guy is called VI, this is equal to VI plus VO divided by what? 2. So if you multiply both sides by 2, you get 2r theta dot equals 2VG equals VI plus VO, and that is going to be this equation. So now if you look, this is one of your equations to solve for omega I and omega O. And the other one is what? The other one is this guy. Now you might say, hey, this guy I cannot use. Why not? Because I don't know theta dots. And you're absolutely right. You don't know theta dots. Okay? So this one only shows me, this one, since it's positive, this one only shows me that since this guy is positive, it shows me that omega O is bigger than omega I, but theta dot I cannot directly use unless I solve for theta dot from this one. I say theta dot is what? Theta dot is VG over R. So I plug in here VG over R. So now one of my equation becomes RT omega O minus RT omega I equals W VG over R, which is this equation. The other one, the bottom one, is RT omega O plus RT omega I equals 2VG, and that's the bottom equation. You see, so I get these two bottom equations, and from these I should be able to solve for what? Both omega O and omega I, and again clearly you see that omega O is bigger than omega I, because the VG is the same, 2RT is the same, but this plus term is bigger than this negative term here. Okay, so these two formulas will give us the required RPM at the left and at the inner and at the outer what? Wheels, and that is the job of the car differential, to make that difference what? Basically happen in a passive manner. Okay. So differential does not control omega I and omega O directly. It's indirectly allowed by the combination of all of the gears in it. And maybe I make a separate video and explain that. But these are the required omega I and omega O if we know what, how fast the car should be going. Okay, what is the speed of the car? This VG is what? This is the car's speed at that moment, the forward speed. Okay, so finally, let's look at what? Let's look at the kinematics, the forward differential kinematics equation. So these are, or differential forward what? Kinematics. These are those equations. Differential forward kinematic. Differential means in terms of velocities, and forward kinematic means going from what is under your control to the workspace. So in the workspace, we have x dot of c and y, x dot and y dot and theta dot. Now you might say, what kind of x and y are these? These are xi and yi. So if you are really interested, which one of those x's are these? Are they attached to the body or inertial? These are inertial. Okay, so this is like xi dot. This is like what? Y I dot. Okay, these are the inertial ones. And how do I find them? Well, remember the velocity of the car is v, And this V is along which axis? Is along XC, but your XC has an angle of theta with respect to XI and 90 minus theta with YI. So this V, if you decompose it along XI and YI, the cosine component will be along XI, the sine component will be what? Along YI, and that is exactly what these two formulas. And theta dot, remember it was VG over what? Over R. Remember here, I just wrote it, I just cleaned it, but theta dot is VG over R, which we just did. So that is your last equation. Now, here, instead of this R, I replace it by L over tangent of correct command angle. So here, look, it comes from there. From here, I can find R. So from here, R is what? It's L over what? Tangent of delta. So I get this R and plug it down here. And you can simplify your theta dot to be what? VG tangent of the steering command over what? L. So these three equations in equation 7, these are the differential forward kinematics equations of what? Of the car, basically car-like robot or any car. So if I have some initial condition, which are like x at 0, y at 0, and theta at 0, and I have these dots, I should be able to what? I should be able to calculate my x at any point, my y at any point, and my theta at any point. Okay? Yeah? And what are the inputs to this system? The inputs are what? Vg, which is coming from the accelerator, and the gearbox, of course, the combination, as well as what? Delta, which is coming from the steering mechanism. So by the combination of accelerator and gearbox, and by the steering of the steering wheel, starting from any initial position, you can calculate your future position or future pose in general. This is the pose of the robot, because you have both position and orientation. Okay, and so we can either solve this 7 numerically or analytically, depending on basically the type of delta we have. Where if this delta is fixed and constant, it makes the life very easy. And also this VG, if this VG is constant, that makes life extremely easy, because now theta dot becomes easy. Theta dot easy means theta is a linear function of time. So this is going to be some cosine of something times t. This is going to be sine of something times t. And we can integrate those to get x and y. So we can have analytic solution if both this delta and VG are what? Constant. So we have a constant steering and a constant speed. But many times it's not the case. This delta, we can change it as we drive, and this VG, we clearly change it versus time as well. So in general, not always we can find this theta analytically. I mean, most of the time we can, but not if these two are complicated functions of time, VG and delta. So here I show you an example where we assume that we can keep them constant. Okay, if we keep them constant, what can happen? Let's take a look before we go to simulations. So here we assume that this delta is constant, or tangent of it is constant, as well as what? As well as VG. This VG is also constant. If that's the case, then your theta dot, which was VG over R, because VG is constant, R is constant, your theta dot is going to be constant. And so we integrate both sides, so theta becomes VG over R times T plus initial angle theta naught. And then we plug them into the first two equations, so x dot is going to be VG cosine of this function, and then y dot is going to be VG times sine of this function. Seems like I forgot to add the theta naught here. I did it afterwards, but here seems like I missed them. Okay, so let's make sure our notation is all good. And again, this x dot and y dot are what? These are the inertial x dot and y dot. Okay, and now if you look, this is just x dot equal a cosine function of time, y dot is a sine function of time, so we integrate them versus time. Your x becomes r sine of vg over rt plus theta naught plus x naught, that's the constant of integration, such that at time t0, this x becomes 0 and y dot is what? You integrated, y becomes this function plus this constant. Now here there is a caveat. These constants are only good when theta 0 is 0. Okay, if theta 0 is not 0, then in general you have to add something because we want x at time 0 to be x0. Okay, so if you plug for t0, then this is going to be sine theta naught times r. So this guy, whatever it is, there will be an r sine theta naught added to it. So what we need to add here is to subtract what? R times sine of what? Theta naught to it. Otherwise, you cannot get it to be all 0. So here I corrected for it by adding a negative r sine theta naught here. So when t is 0, the x becomes x0, and when y at t of 0, so you plug in a 0 here for t, right? This guy becomes negative r cosine of theta naught, so I added that plus term, so at t0, y is equal to y0. Okay, so now these are more accurate, and from here, if you take these two constant terms and take them to the other side, the same thing with here, take these two terms and take them to the other side, then square both sides and add them together, you get r times sine of this guy squared plus r squared times sine squared plus negative r cosine, the whole thing squared, so it's going to be r squared cosine of this angle squared, so it's just going to be r squared. So you get what? You get this equation, which is clearly the equation of a circle. So if you hold your speed constant and the steering angle constant, you definitely are going to go on a circle, where the center of the circle is basically this point here, right? So it's going to be this guy with the negative sign, that is the center x, and this guy with the negative sign, that is what? Center y, and the radius is going to be r as expected. Okay? And how much time does it take you to go one round around the circle? Where here, if you look, the frequency of these harmonic functions is what? Is Vg over r. That is your omega. And so the period is 2 pi over omega, and that's 2 pi over that guy, so it's going to be this. So this is the time it takes you to go over that circle one round, okay? It takes you that much of time in seconds. Right? So you got some good formulas here. And now let me show you the simulation. So here we assume you are going around the traffic circle, where the size of the traffic circle is 250 feet in diameter. I got this data from internet. So the radius is 125, and I converted it into meters. I'm doing everything in SI units here. The radius of a tire average I found to be about 25.4 inches, so I converted it into, first I divide by a 2, multiplied by 0.5 to make it radius, then this is inch in meters, and for a basic sedan car I found the track width to be 1.8 meters, and the wheelbase to be what? About 4 meters. And here we assume that you are going with about 15 miles per hour around the circle. You're not going to turn the circle very fast, which is equivalent to 24 kilometers per second, or if you want to convert it to meters, kilometers per hour, if you want to convert it to meters per second, then you divide it by 3.6. So this is Vg in meters per second. Then here you calculate the actual steering command that you need by arctangent of L over R. This is the actual angle that you should be steering. But here, this delta is the one that you really are going to give to the steering wheel. Okay, so this is the required one to go perfectly around the circle. This is what you practically give it, which could be equal to it, less than it, or bigger than that. So you are free to change this number as you wish. And then here, based on those two formulas I showed you, these ones, 2 and 3, we calculated the inner and the outer wheel steering angles based on what we physically really give it. We calculated the steering ratio, this gamma here, and then we went to use these equations in 6 to calculate the required RPM. So here I just directly solve for them, but if you want, you can simply go ahead and apply those formulas. So what I did, I solved for these two equations. But if you want, you can directly plug in these two formulas in 6 to get omega I and omega O. And finally here, I'm starting from some initial conditions. And I assume I'm going to go around the traffic circle here with a radius of R, as I said. Okay, so I have a traffic circle here. And I'm going to start on this right side. And I'm going to keep going around the circle. Right, so here this is your xc, this is the direction you're going to go, and this is your x inertial. So your initial angle here is 90 degrees. Okay, that's your initial theta, which I have in the code. And my initial x is r, my initial y is 0. So the center of xi is at the center of the circle, and this is yi. Okay, yes, so this is this point here that you start, this guy, that is at x of r and y of what, and y of 0, and we start at time of 0. And then this tf here is the same as this capital T that we have, the time that you need to go around the circle one time. So we use this formula. So the goal is to go around circle one time, and here, since we are numerically solving for it, instead of analytically, we use a sample time of 0.01, and here we are solving for those equations using the Euler method here. Euler's method. And you might say, why don't you solve it analytically? Well, we can, but here my goal is, if you come back to this code, and if you want to change this delta over time, or change this VG over time, you should be able to do so. Okay, so if you want, instead of a fixed VG, and instead of a fixed delta, what you can do, you can come to this code here and say what? And say, hey, delta II equals something, whatever it is, and what? VG equals what? Equals something else. Okay? So here, you can basically, right? Or you don't need even II, you can change them as you need. Okay, so if you want, you can change them within the loop. Like in real life, you're adaptively changing your speed or adaptively changing your delta. So you can change them within the loop instead of keeping them constant. That makes your animation a lot more interesting. Okay, so now let's just run the animation. Let's take a look. There we go. So here, the blue is what you really wanted to go through. It's a traffic circle that you really wanted to go through. And the black is the one that you're actually gonna pass through or traverse. The red is the car. And the reason for that is you needed about 6 degrees steering, but practically what you're doing is 5 degrees. Okay, so you did not turn the steering wheel enough. You needed 6 degrees rotation, but you are turning 5 degrees. And for that reason, you have to go on a bigger circle. And for that reason, the time that you needed to go over this smaller circle to go one full round, now if you use all that time, you cannot go one full round. You're gonna go here like something like, I don't know, like 5/6 or something like that. 5/6 of the circle or so. Okay, yeah, do you see that? That's because I'm not steering enough. Now I can go back here. By the way, all of the results of the code are shown here for you. You see? Here, this is what you really need. This is what you physically have. This is the inner wheel steering angle, the outer wheel steering angle, the steering ratio, as well as the required RPM for the outer and inner wheel. These are in RPMs, by the way. I converted them into what? Into RPMs. And you can see that here when I calculated these omegas. Let's see. Here. I multiply them by 60 divided by 2 pi to convert them from radians per second to what? To RPM for you. Okay. So here is very interesting. Now you might say, what if you go what? Instead of 5 degrees, you go 8 degrees. Instead of command 6 degrees, now you turn a little bit more. You turn 8 degrees. Well, see what happens. Of course, you're going to go on a smaller circle. Look here. The blue is the real one that you want to go, but now you're going to go smaller. So what happens? You're going to drive into the traffic circle. You probably have seen people that do that, huh? Yeah, they don't go the full circle. They kind of pass over that instead of around it, right? Because they steer too much, or they were going too fast and they could not control it. Yeah, so you see clearly that you're not doing it. Now, on the other hand, if you say this delta is equal to the delta command, well, I exactly want to go as I'm supposed to go. Now you go on the perfect circle. Look, you see? Now they're on the top of each other. So you go as intended because you exactly use the required steering angle. So as I said, you can come here to the code, and I don't do this part for you, but you can do it yourself. You can adaptively change this delta or change VG here, right? So you can see, for instance, if for this delta, let me show you just a part of it, just so you have fun here, right? So if you come and change this delta, so you say delta equals what? Equals, so here I add some randomness to it. I assume that you are just steering left and right a little bit, right? And you're turning your steering wheel. So what happens? I add a little bit randomness to it. And now you see that, look at your path, right? So first you're going on it. Now you go into the traffic circle, you go, and then now here you get out of the traffic circle, and then you go back into the traffic circle. Right? So this is kind of like people are under influence, driving under influence. So you see, now you see some crazy behaviors, right? Or you can do a similar thing with velocity. You can do some randomness to the velocity and so on. Okay, and you can make it more interesting. And if you want, you can also, as I said, really use Runge-Kutta method or anything, okay? Because this Euler method is good when this dt is very small, okay? And this might not necessarily be a super small number when these conditions are changing versus time or so. Okay, so you might change this to Runge-Kutta or so on and make this a lot more interesting. So I give you a download link under the video description, and feel free to download this file and play with it and learn from it. And let me know if you like this video or not. So hopefully it was useful to you and you liked it, and I'll see you in the next video. And this video was long in my to-do list, so finally I could get it done today. Thank you.